So I wanted to comment a couple moments about the homework and also looking at the class schedule again. So for 523, this is sort of the updated schedule, which it doesn't seem to be updated. I'm not sure whether this is cached. Let me I meant to put the chapter 5 notes on, so I'll post them tonight, so you may not be able to follow along. I meant to post the chapter 5 notes right here. Okay. So, looking at the two assignments, one which is due this Friday, and then if you think in terms of S3 classes, it's sort of a translation you have to do in your mind to go from an S3 class to an S4 class system. I think once you figure out the S3 class system, that going to the S4 is not so difficult. But in terms of this assignment 3, I had several examples. Where did I have the leash notes? Oh, here. Yeah, these two examples right here, the t-test S3 and the linmod S3 are both examples of how you implement of something similar that I want you to do for the one way. In other words, the two-sample t-test is done on the t-test S3. And that shows you how to develop a t-test implemented with various methods using S3 classes. The linmod is a little more complicated example, but it gives you a second example where you implement this using S3 classes. Now, S3 classes is kind of an informal way of doing things, and when you look at, let's take this and blow it up. So what I'm going to do is the 523 notes. See, under chapter 3, I have both, I have the t-test, and then I have, here I have both the S3 and the S4 here for that particular one. But just looking at the code, I'm going to define something called t-test, and notice that that second line you don't actually need to do, that's sort of a check, but the use method is critical, because the use method is what's going to let me dispatch depending upon the argument, the first argument. And then I have this default, which t-test.default, and I'm going to have various other methods, but notice that in particular I have a t-test.matrix, t-test.list, and a t-test.factor. Okay, so all of these ultimately they ultimately work back to this t-test.default. Okay, so one of the key things is this statement right here. that is what gives the class definition to results. And that's critical. Otherwise, it's not a class. In S4, you up front, you say set class. You define it formally. You define the slots formally. So it's a much more formal system. This is kind of a, it turns out this is, well, on the surface it appears much easier, but once you do a few S4 classes, I'm not sure that they're that much more difficult than S3. But at any rate, look at the t-test, study it, study the Lin mod, and then hopefully that will give you some guidance into what you need to do go one way. By the questions, I sort of stepped through it, but my understanding is that at least some of you are struggling a bit. Is that a correct assumption? So try to work on it. Try to work on it as much as you can to get it working. Try to follow along. I sort of outline it question by question, in terms of how you do it. And that's true for the S4 classes also. You may want to look at the S4 classes to give yourself some insight as to what the differences are in terms of the way you implement it. And again, I gave several examples with S4 classes. So, yeah.
With the testing, do you want us to test at a critical value, or would you just want like the p-value?
Usually you just give the p-value. The critical value is more of something we teach in SAP 211. You almost never see that. Computers always give p-values. Then if it's less than 0.05, that's equivalent to testing a critical value of 0.05.
Because you may want to add arguments to some functions like alpha is 0.05.
Yeah, that's maybe legacy. I'm not overly concerned about that. When you're doing the LS means, I'm going to permit you to use pairwise.t.test. Okay, but if I were comparing multiple comparisons and I have G groups, okay, let's say G equals 5 or whatever, then I'm comparing the first group versus the second, the first versus the third, the first versus the fourth first versus the fifth, and so on. So how many things are there? If you had 5, how many comparisons are there? Does anyone know? There are 5 things taken 2 at a time. So it would be 5 times 4 over 2 or 10. It's sort of like you have the lower triangle. If you think of a matrix, if you had A, B, C, D, E representing the 5 groups along the rows, and A, B, C, D, E representing the columns, then you would either have the upper triangular or the lower triangular. You would not have the diagonal. And so if you did it in a double loop, you could go from I equals 1 up to G minus 1, and then from J equals I plus 1 up to G. Does that make sense? So you have an inner loop of J and an outer loop of I. So if I goes from 1 up to G minus 1, and then J goes from I plus 1 to G. So when I equals 1, the first J is 2, the next one is 3, the next one is 4. So I'd be comparing 1 to 2, 1 to 3, 1 to 4, and so forth, up to 5, if there are 5 groups. Then I'd go, now I increment my outer loop. I goes to 2. Okay, now J starts at 2 plus 1, or 3, so I'm comparing 2 to 3, 2 to 4, and so forth. So if you did it with sort of a nested loop, So you have an outer and inner loop. You get either the upper or triangular. The way I did it, you're going to get the upper triangular. But you can define a corresponding thing that would give you the lower triangular, which is what pairwise.t.test does. You could look at the code for pairwise.t.test. I think it's given.
You can see it.
Why now?
You can see it if you type in the name.
Yeah, that's what I'm assuming you can. Let me get rid of that first. So pairwise. Okay, I am recording. I just want to make sure. Now they have a lot of checking. They have a lot of checking on, but you can look and see how they did it. In other words, here's x bar I minus x bar j, but they're doing it. They have a function called ij. They have a function called ij, and then there's something that calls that. I forget where it is. But there's something that calls this function ij, and I forget now what that function is called. But this is a little more complicated than, obviously, what you would need to do if you did it by hand. Okay, so in other words, they define a function here of I and j, and then that gets called. And I'd have to look and sort of, we don't compare levels function. Okay, that's I and j. And I don't want to spend the time looking at it, but that gets called as a function of I and j. But again, you can sort of see the calculation here for the p-value, including the p-value. So if it's one-sided, two-sided, and so forth. So they have the difference, and then they have the standard error of the difference, which is the pooled standard deviation times the square root of 1 over n sub I plus 1 over n sub j. So you can sort of see these, and then it gets the t-value, and then it computes the p-value from that. So the basic calculations are there. And also up here, they're showing the calculations for the pooled standard deviation and so forth. So right in here is all the calculations if you want to do it. And the way you could do it is have an inner and outer loop. So you have 4I equals 1 to g minus 1, 4j equals I plus 1 to n, with basically this in the inside of the loop. Do you follow what I'm saying? If you want to do it by hand. Any questions on the homework? Any other questions? So, what I want to do today is go back to chapter 4 for a moment. And again, I wasn't going to spend a huge amount of time on chapter 4, but I want to spend a little bit more time. I'll set the working directory and let me see what the workspace. I'll get rid of that. Okay. So last time we had done quite a bit of this. I think it was right about here that I stopped. I talked about a text connection. Did I talk about a text connection? Yeah. I talked about a text connection, and then I talked about sync. And sync, again, sort of syncs the output into this file, and then you can turn off sync ultimately. And at any rate, it's a way of saving everything you do on the screen. Now, you have a history mechanism. That if you type at the console, every command you type gets saved into a history file, which you can look at. and in particular, in RStudio, the history is right here. So this sort of gives you recent stuff you've done. And I think you have some control over how long you keep the history going. But that's what you do at the console. The sync is the same thing. It's what you're doing. It's what you're doing. But in the sync, you can actually write a program and you sync it into some external file. And then you can sort of play it back. One of the things that we're doing in the software we're writing is that we have the capability, well, we don't yet, but it would be nice that if every command you do in R gets synced, but it's also recording my voice that synchronizes with those particular things. So in other words, as I do commands, it syncs the commands and the output, but it also syncs my voice with the commands. That's actually what we're trying to do. It's not as hard as it sounds. Well, it's not trivial. But at any rate, I want to talk about a little bit about interprocess. I want to talk about interprocess communication and sockets and pipes. And so, but there's not much here. So I'm going to go back and talk about a couple things. Does anyone know what a FIFO file is? Yeah, it's first in, first out. In other words, as you push things in, as you pop them out, the first thing in is the first thing that pops out. So you sort of have a push and a pull operation. You push something into a file, and when you pull out, under the FIFO, the first thing you pop in, then it's the first thing that gets pulled out. And so there are ways of doing that in R. And in particular, you're using the file system. But you may not want to use the file system directly. You may want, in Unix, we have this concept of processes that are running simultaneously. So you have a process over here running, a process over here running, and you'd like them to be able to communicate. So this process can typically we have it sort of a server client or a master slave, so that the process is not necessarily sort of bidirectional. In other words, there might be sort of a server type and a subservient slave or client. So the FIFO is something that you might be interested in doing, but more generally, we want richer ways of doing things. And so I had showed you the connections, and this depends. You always will have standard input, standard output, and standard error, because standard input is sort of getting things. It's how you get things into, say, the terminal, and how you print things. And then standard error is where you print, errors if they occur. But you can have other connections that you define in R. And so I had defined this text file as a connection. And so you can have other connections in addition to the three that you're pretty much always going to have. I think you always will have. The capabilities just tells you, can your machine do JPEG, PNG, Tickle, TK, and X11? X11, by the way, is the Unix windowing system. So obviously on our Linux server, then X11 is true. That is the native windowing system of Linux. Now the Mac OS can run both windowing systems. It's its own, which is what most people think of as the Mac. But it also can run X11. You may not know this, but there's an open source called Darwin. And Darwin is actually all the Unix part of the Mac. And you can actually download that with X11 and not have any graphical interface that you would recognize as a Mac. I'm not saying you should do that. I'm just saying you can do it if you want to play around at the kernel level and stuff like that. At any rate, I talked about text connections, which formed a new connection. In this case, we formed a connection called letters. That's a text connection that allows you to read lines and write lines and scan and so forth. And then again, this is where I talked about creating files using the sync command, which then you can play back later. So what about interprocess communication? Again, in Unix, you have running processes, and you might be surprised under the hood. You might be surprised how many running processes that you have going on. There are quite. If you go to the terminal, you can actually see that there are a lot of processes that are sort of running in the background, and that's actually true. If you have an Android tablet or you have an iPad, they're both Unix-based, and they have all these processes that are running in the background. Now, you're typically not going to know this, but they're there. And so the idea is, how do you communicate? How do you communicate between processes? And there are various ways in R we can do this, using there are various ways to do it. One way is doing it with a socket connection, and in R, that's the common way of doing it. The socket dot connections, which I don't know if it's supported on Windows. It didn't used to be, but it may be now. I haven't checked it recently, but it is supported on any Unix-based system that you have a socket connection. All of these things actually originated in Unix back in the early 70s. I'm not sure exactly when it started, but it was pretty early. So for example, I'm just going to do this here just to give you the idea, but I'm not going to, spend a lot of time. You could form a socket connection on a certain port and as a server, and so we have something called server connection, and then I could write to it, and then I could close it, and you can have a client connection on that same port, which can read from the server. So basically what's happening is you can write to the server and then you can read it. You can read from that server connection. And then ultimately you'll close the client too. So these types of connections are quite powerful. I had shown you the software we're writing, and we actually have, like when it runs on the iPad, that's the client, and then the server is running on the server. And so when they communicate, we're doing this type of connection where we have a connection between the two devices that they're talking to each other and pulling stuff back and forth. So when I have a command on the iPad and hit execute or whatever, it sends it to the server, and the server executes it, and then it pulls it back. And so it's using connections. Now, there's something called WebSockets, which lets a web browser do this. And so you can actually have a web browser as a client to R that's on a server. And so you can have interprocess communication from a web server. And there are several people that have done that, where you can run R within a server. We actually started doing that. And we're kind of holding off on that for a little bit now because, that's basically the way Google Docs works, for example. There's a server and a client. And so, and what happens when you do offline editing of a document in Google Docs is what happened. It's pulled a copy down and you're editing. It saves it locally. But then as soon as you connect it back up, then it pushes it back up to the server. So the problem is that it's like Google Docs. It doesn't necessarily have the prettiest interface, and part of the problem is that, and it's getting better, but the part of the problem is you're using something like JavaScript on the client, and you can't do as much in JavaScript as you can using the local APIs or the local programming interfaces for like Android or the iPad. So if you try to write a really, really nice program within a web server that's communicating with some server that's sort of a back-end compute engine, you're not going to have the prettiest interface. I mean, you can do quite a bit, but it's not going to be as nice as a native version, and it's probably not going to be as fast. Well, it won't be as fast, almost certainly. Okay, so pipes. When you have pipes, when you have one process, I can put a vertical line. I can write on a terminal. I can say, okay, I can write a command, and then I can pipe it. I can pipe it to another command, and what it does is the output from one command gets piped as the input to the other command. And so I think I mentioned this is how you can set up a workflow. So you have a map and reduce. So the output from map gets piped into the function that does the reduce. And so the output of one flows as the input of the other. So you can chain together all these commands, and it forms a workflow. And then one of the things you can do from the terminal is you can put this all in the background so that it's running in the background, and so ultimately it can notify you when it's finished, but it might run all night. You may have, if you have a large Hadoop job, with a petabyte of data, you have a huge amount of data, so you run this map reduce operation. If you were running it using Unix piping, then it could take a long time. Now, of course, that's not actually the way Hadoop works. The way Hadoop works is you have this whole cluster machine, and it splits the job up, and then it reassembles it. And so with Hadoop, it actually does it in parallel. So it still might take a little bit of time, but it's going to be much faster. And some of the, you can imagine that Google and Amazon and so forth, when they talk about a Hadoop cluster, they may have tens of thousands of nodes. What do you think Google's doing with all the data it collects from you? Hadoop is, well, or their version of Hadoop, is crunching it. So you can do very sophisticated things. A lot of the examples in Hadoop seem rather easy, but there's a book which is actually free, except I can't remember. No, that's not it. At any rate, there's a free book I might show you sometime for those of you that are interested. I don't see it. For some reason, I don't have it categorized under Hadoop. Maybe it's under big data. Nope. If I find it someday, I'll show it to you. It's a book on data mining big data. And it's a very interesting book. It's written by two professors. This is free. I mean, you can get the PDF for it. And it's a pretty long book, like 300 pages. But it talks a lot about using Hadoop for data mining. Now, this book has some bioinformatics and genomics in it, and we're going to talk off and on today about sequence data. So you have a genome and you have a sequence representing the 4 letters of the alphabet. And so if you're looking at letters of the alphabet, there's a type of data mining called text mining. So we're actually mining the text, in this case genomic text, to try to find patterns, for example. And so this type of thing, this is alluded to in the book. Okay, let me go back over to, if I can define a pipe, so if I define a pipe, and I say pipe is Cal 1 2006, what do you think Cal means, C-A-L? It means calendar. And 1 is January of 2006. And so if I look at P1, this is giving information on the pipe, and then I can say read lines. And this doesn't show you the full thing, but you can see that that has actually created character strings. And notice that the first string is January 2006, and then it gives the days of the week, and then it gives the first 7 days. And so it's actually giving the month, but it's not quite in the right format. But there is, but you could format that. You could format that so it looks like a calendar. And in fact, they did this in a package called this RBioInf, which we've used several times. There's actually a package that, I'm not sure where I put it in this package, but it's here. Maybe you need a calendar when you're doing bioinformatics. At any rate, there's something called rcal. And so rcal is a function, and you can look at that function. It's formatting the calendar, and that's what it looks like when you format it. This particular one is, why is it April? By default, it looks like it's giving, why is it giving April? That's interesting, because P1 I had defined, well, not sure why it's April, but I'd have to look at the code to see what happened, perhaps. You see, you can give as an argument the month and year. And it seems to me it should have pulled those out. I'd have to look at the code to see why it's giving April. At any rate, in general, this can this is a little function that took the output from pipe and actually gave the month and year, although perhaps not what you were expecting. Now, I can also, this system is a systems command. The ls -1 is a Unix command, and that's given in quotes. And so, so we could ask, well, what's WW? It's actually giving what's in my directory. So that would be equivalent to bringing up a shell by print working directory. Okay, I'm in chapter 4, and that would be equivalent to doing this. What did I do? Oh, it says minus. Well, that's the long form of it. That's not a minus, it's a -1. If you just do ls by itself, it gives this. So, and the only thing I'm trying to point out to you is that you can actually give Unix systems command embedded within your R code. Now, this is something that we are disallowing in the software we're writing. So why is it okay here in RStudio, and why is it maybe not a good idea in general? In RStudio, you're sandboxed within your own account, because you actually have to have an account to get into here. And if you want to mess up your own account, you can, but you can't mess up. You can't get out of your sandbox. So you can do anything. There's an RM command which means remove, and there's a recursive version. There's like a -R, RM -R, which is recursively remove. So you could go in and give a command that recursively removes every file in your home directory. you're free to do that. I would be very hesitant to use the command rm-r because if you're in a there are reasons why you might want to use it, but you need to be careful in general because it recursively can remove up the tree and essentially wipe out everything you've done. So you could think about a virus that infects your machine at a fairly low level, and if it could recursively just remove all the files, you're in trouble. So the problem is in our system, we don't sandbox you. Because we don't, we are not allowing you to do these types of Unix systems commands. Or at least the ones we let you do are going to be innocuous. At any rate, that's not the case here. You can essentially run any Unix command within R. And there are reasons to do that because it lets you interact directly with the file system. So there are reasons why you might want to do that. Okay. I can also do this with a pipe, and I get the same result.
Do you mean to put that -1 there? That's supposed to be an L.
Yeah, I think the -1 will give the same results. It's something I never use it. I always use -A, -L, or -AL, depending on whether I'm with the dots or not. I don't know that there's any advantage to using the -1. By the way, if you're in Unix, you can always get help by saying man ls, and then this gives the help man for manual, and then this gives the help. That you notice I said that if I give ls, I can give options like -A, . So if you look here, -A means everything. Okay, and if we go down here, someplace with -L is use a long listening format. But you can see there are tons of choices. This is why Unix can get difficult. And no one is going to, that's why manual gets used a lot if you're doing something esoteric. But if you're doing the common types of, if you're doing ls, you're almost always going to do -A, -AL, or -L. But there are many other things that you can do. All of these are different options. So, see, -A, almost all. Do not list implied. You don't list a dot and a dot dot. By the way, the dot means the current directory. If I'm in a directory, the dot means that directory. Dot dot means the parent of that directory. It's a hierarchy, remember. So dot dot is the parent of the current directory. So. So at any rate, if you want to look at Unix commands, this is not the best way to learn Unix. You probably should buy a book because you would go crazy. If you just tried to learn it this way, you wouldn't know which of those options are important and which aren't. But if you read a book, they'll tell you, okay, here are the 3 or 4 options that are really needed. The rest of them you'll rarely need. Look them up. Okay? So, I was going to, some of these don't work. I was going to skip this part on seek because I want to move along a little bit. I want to see if this works. Read lines. I'm going to form a connection. This system file contents. I can't remember if that. No, that one is not working. See, as I said, you'll see later on when you write a package. And this package is the base package. I mean, it is the fundamental package in R, the base package. And there's always a specification for the contents in that base package. And what we were trying to do is retrieve it. But apparently, here's the problem with that package, is that you don't have read permission. So maybe he does on his machine, because he's one of the key R developers. So he probably did have permission, but we don't have permission to go in and read that file. But if you write a package, you will have a contents, and you will, in principle, be able to read it if you know where it is. So I'm gonna skip over that. I just sort of mentioned that in passing. So. Just trying to decide what I want to skip and what I don't want to skip. I guess I can quickly do this and see what it is. This is a temporary directory, and then I can actually go through this, and I forget what this does, but it's not actually writing anything. It's just a for loop, but it's not writing anything, so I'll skip that. Now, I don't have examples here, but a lot of times you have data and you want to read it in. As a rectangular data set. And so this read.table is very, very common. But you can have other delimiters, and for example, if it's comma separated, you might say read.cbs. So you have a text file, and it has columns, and something separates the columns. And so you want to read it in that way. So, for example, what I did in my other class, I'm trying to remember which function I did. This is going to mess me up, but if I go into if I go into here, into 512, and if I go into this section, I think, and someplace down here, I may need to change the directory to do this temporarily. I have a data set that's in a text file. And just to show you what that text file is, this is what the text file looks like. That's just a text file. So how do I get it into R? That's what it looks like. There's a header, and those are really the variable names. And then this is a 3-factorial experiment. I have 3 factors, and this is the outcome variable. That's viability. Okay, so that's the text file. So if I go into here, I can read it with read.table. I say seaman.text, and header equals true. The reason I say header equals true because the first line are the variable names. Otherwise, we're treated as data, and you'd be in trouble. Okay. So I have header. So I can read that. So if I run that, I read it in. And then if I say head of that, the head prints the first 6 values. But I'll go ahead and print the whole thing. So if you look at it in R, there's the whole file. There are actually 72. It's a 3x2. It's a 3x2 by 3 factorial with n equals 4 replicates for each of the combinations of the 3x2 by 3. So 3 by 2 by 3 is 18, and 4 times 18 is 72. So there are 72 observations. So as explained in my last class, you can think of it as Rubik's Cube, which is 3 by 3 by 3. And if in each of those cells you had 4 observations, you would have 3 times 3 times 3 times 4 total observations. In this case, it's sort of a Rubik's Cube that's missing something. It's a 3 by 2 by 3. So the rows and columns and depth, it's 3 rows by 2 columns by depth of 3. So you have 18 cells, and if in each cell you have 4 observations. Okay, so you get a total of 72 observations. So we had that in a text file. Now, you can also import it from things like Excel. So you can go in Excel and you can easily create these types of files. But another thing you might want to do is put commas between. If I look here, can you tell me why you might want to put commas here between the values? Well, you could have missing values, and if you just use spaces and you have a missing value, you could be in trouble because there's nothing to tell you how many columns you really have then, so you could get out of sync. But if you have commas, you could have a comma, comma. That means you had a missing value between the two, right? So a lot of people use comma-separated values, and you can take Excel or you can take Jump, and you can create these comma-separated values in either of these, and then you can easily import them into R. Now, R has direct connections to like SAS, so that you can directly take what are called SAS data files that you output from SAS, and you can actually read it directly in. But read.table is important. The other one, as I said, that's very important is read.csv for comma-separated values. So if comma separated these, I could read it that way. And then comma.delim gives you a lot of choices for other delimiters. I mean, you could use a colon as a delimiter between the values if you wanted to. So the table.delim gives you more flexibility. Now, when it comes in, it's coming in as a data frame. I now have a data frame. So. The data frame. Any of you know Python? Python is becoming a very popular language. In fact, I hear that the CS department is thinking about dropping, maybe I'm going out on a limb here, but is thinking about dropping Java as a primary language, the first language you learn in using Python. Whether or not that's a good idea, I don't know. I don't know if they're going to do it. I just sort of knew that they're thinking about doing it. At any rate, Python is actually a little more accessible than perhaps Java is. Java at this point is used widely on the server side, but not as much on the client side anymore. And so I think some of the people that really started pushing Python were the physicists. I don't know if that's the best choice or not. Physicists have very big data. A lot of times, huge amounts of data. And so apparently it must work okay. At any rate, let me go back. I was just showing you the read.table. And so I need to actually go back and reset the working directory. If I don't reset the working directory and I need a file, it's not going to find it. So that was the example I gave of read.table, but the example of read.csv would be essentially the same, except that you have commas separating the fields within each row. So you read them row by row. Read lines also reads row by row. I mean, there are other ways you could do it. You could do read lines and sort of, you could do it with read lines and sort of create your own data frame, but it's a lot more work.
If you do read.delim, do you have to specify what your delimiter is?
I think they have a default, but let's. What now? Yeah, they allow you to. Why is this not giving it to me? Read.delim, that might help. Am I not spelling it? Yeah. What's going on? These are all choices, I guess, but I was hoping to just. What now?
That's the history of the help.
Oh, I'm in the history. Ah, okay. This will help. This will be better. Yeah, I switched over to the history at one point, didn't I? Read.delim. Okay. So it's going to tell you what the well, this is read. This actually is giving everything. I mean, it's giving all three of them here. Okay. But notice that read.csv by default has the header equals true. So But notice for read.table, the header is false. So you have, if you have a header, you have to say header equals true for read.table. Okay. And then, for example, read.csv by default gives you a separator of comma. Read.csv2 is actually giving a semicolon. And then read.delim is by default. /t means tab, so if you tab between them. But if you do if you just use white space, which is what that's saying, if you're just using white space in between and you have missing values, using read.table at the default could be a problem. Okay. That's why a lot of people use this comma-separated values, in case you have missing values. You know, I don't know if you've used jump, but when you read in a text file, one of the options you have is best guess. It tries to sort of scan part of the file, and then it makes a guess as to what you want. But it doesn't scan the whole file, I don't believe, and therefore, if you have missing value down below, and if it scans part of the file and doesn't see a missing value, but you have one below, I think you can get into trouble in jump. There are ways around it, but... Okay, any question? That's fairly important. Oh yeah, there's a help command here. That's fairly important, you know, to know. So, let's see. What else do I want to cover? This Debian control format is something that actually doesn't work here because I forget why, but it doesn't. But Debian control format you can read about in the book. Debian is a type of Linux, I mean, and so it has a format that's sort of been accepted as a standard. This particular format, so you can take a look at it in the text. Perhaps more importantly is the FASTA format, and so if that I want to look at just a little bit. It's down here a ways. This shows you what you should get if it would actually work, but it won't work on yours. FASTA is part of the it's a standard. It's a standard in biology for sequence data, and so what it basically does, it starts out with a greater than sign, and then on that first line, you may have some other information. Each sequence is preceded by a single line beginning with a greater than sign, which provides a name and/or unique identifier for the particular sequence you're looking at. And it may contain other information. And then you can have some comments, and then you actually get the sequence data. So in other words, it provides a way that you put the name of the sequence or some identifying information, and then you have comments about it, and then you're going to have the actual sequence data. So, I don't know. So if you go to Wikipedia, there's an example where there's the first line, and then this is the sequence data. Now, it's not necessarily the sequence data of the genome. It could be the proteome. In other words, it could be for the proteins. And proteins have a much larger alphabet. What is it, 20?
Yeah.
Proteins have an alphabet of 20, whereas genes have an alphabet of only 4. So that's an example. So there are these databases out on the web, and so in R we can connect to those databases and pull it in, and then we can analyze the sequence data. Now again, we would have to know, that's identifying that. If you are a biologist, can you tell me what some of this means? I don't know if it's species information, perhaps. So in other words, they have identifying information in that first row, and then they have the sequence, and I think that is a amino acid, or that's a protein sequence. So at any rate, and once we bring it into R, then we can use character manipulation, which is the next chapter, to analyze this. So what do you want to do? You have this really, really, really long sequence, say a genomic sequence. Well, you might want to subset it. You may have another piece, and you want to sort of match it. You want to find, okay, I have this sequence that's maybe a gene, or some sequence, and I want to match it to this much longer sequence. So I want to be able to match, and I may even do it in such a way that it only partially matches, because you may have genetic variations within the gene, what are called alleles. And so you may want some way that you have some flexibility in how you match. But you may also want to compare two long sequences and find out where the differences are. So if you had sequences from cancer patients and sequences from normal patients, and you were looking at certain genes, you may want to identify genetically how those two patients differ by perhaps it's some mutation. So at any rate, that is the FASTA format. It's not the only one, but it's very commonly used. And if you can start out by reading here, and this is actually giving like the amino acid codes and so forth. So this is actually a place you could kind of get started in. So going back to this, a lot of these things. This particular section, 4.6, which is discussed, where is it? Right here. This is something that's spent a lot of time on in Stat 623. So you've got this big web out here, and you want to go out, and we do what's called web scraping. We pull information in, and then we process it. Now, one of the very powerful tools is curl, C-U-R-L. And the URL is, do you know what URL is? Curl the last three letters are URL. And that stands for a Uniform Resource Locator. And that's how you identify web pages and resources on the web. And so, so if I wanted to go out and scrape the web and pull information in and then process it in R, there's a package called rcurl. And rcurl sort of is an implementation of R, which is curl, which is a Unix-type implementation. So it's extremely powerful because I can go out and pull information out from the web and then process it however I want, and then do analyses on it. And so that's what people do this. So if you post stuff up on Facebook, be cautious. There's a lot of reasons you should be cautious. I don't personally recommend Facebook for you. Anyone who's going to hire you is going to look at your Facebook page if you have one. So you better be careful about what's up there. And it's not as easy to erase as you think. You can erase it, but it already may be spread. Even if you erase it, if someone else has captured it and posted it elsewhere, you can't get it. You'll never get rid of it. Anyway, there are a lot of protocols, and rcurl supports essentially all of these. The interface in C is called the libc curl. Lib for library, C for the program in C, and then URL. There's a huge library in C. And what rcurl does is access that library. So if you don't know anything about the protocols used on the web, then there are some important ones. FTP, File Transfer Protocol. A Of course, HTTP, you use that all the time. That's the web. There are secure versions of FTP. Gopher is a protocol that's not used as much, but it used to be used quite a bit. Telnet, again, that's a communications with a terminal over the web, and that is, we use more sophisticated versions of it. So if you're at home and you want a terminal connection, so you're using a more sophisticated version of that. It's like SSH, and then you log into your account. SSH is secure shell. It's a much more secure than, and then you put in the password. And I'm now in my account, and then I can look at it and do stuff. And I can run R here. This has low bandwidth. You can run SAS this way. If you log into the SAS server, you can run SAS this way, and it has very low bandwidth as long as you're not doing heavy duty. I mean, this is the way I prefer to run SAS. I hate running SAS with the interface that SAS gives you. You know, they have a multi-windy system, program editor, log, output. It's very, if you try to do that from home, it's slow. This, running SAS, fast. Because it's lightweight. And then you can create a PDF file, and in R, you can do this in R2, you can create a PDF file, and then you can actually open it fairly quickly. Okay? So this is another way to run R. And so I could run this R this way, and then I can run it in RStudio, but RStudio is a fairly complicated environment too. And so I could go into R and run a terminal session and scrape the web, pull it in, do whatever I want. And we do some of that in sets 623. So I'm just telling you that we're not going to do it here. Anyway, there's a library R curl. This may or may not work. I don't know. It depends on whether that link is still there. If that link is still there, it will work. So if you're interested, you can kind of take a look at it. I haven't checked that. I haven't checked this. This is an FTP site. It means that's a site that has files. FTP means it's not secure. It's not secure FTP. There's an S FTP, which is secure FTP. The university doesn't want you to do stuff that is not. That's why we have to do secure shell. SSH means secure. So we have to do it. We can't go in non-securely. The university gets upset if you do that kind of stuff. Okay. Any questions? Again, I was just giving you a few highlights in that chapter. I wasn't intending to do everything. Okay, now, in this particular chapter, there are some biological packages we need. Remember we have this bioinf, but there's a biostrings. Some of these are not installed. This is installed, I'm pretty sure. Biostrings and annotate are installed, and I think one of these is, but this particular one is not. That's not, and I think maybe this is, and this is not. I will have Steve install all these packages. Because as we go through the chapter, we may need a few of these. So at any rate, what we're going to do, first of all, I meant to post this for you. I apologize for not doing that. We're going to talk about some built-in capabilities. We're going to be talking about string manipulation. So why is this important in bioinformatics? Lots and lots of strings. DNA strings, protein strings, and so, you know, it's something that's widely used. And so therefore we need to know how to manipulate data. So in section 2, we're going to be talking about sort of built-in functions. And we'll do a little bit more of that today. And then we'll go into a topic that's more advanced, which deals with what's called regular expressions. Now, when we're parsing things, we use regular expressions a lot. And the bad news is that regular expressions sort of come from the Unix world, and it's very cryptic. The good news is it's very powerful. And regular expressions are used a lot when you're studying biological sequence data because it's so powerful to be able to manipulate strings. But R has some functions that use regular expressions too. So let's go into chapter 5. We'll just spend a few minutes today getting started. I need to go back here into notes, and I'm going into chapter 5, and I'll bring this up. Actually, this is chapter 5, section 2. Okay, we may need this library, BioInf. I don't know if we probably won't get to it. I'll go ahead and run it. Okay, it's closing certain connections. Okay, so suppose we have a vector of character strings. And so if I run that, so then the question is, what is this? Well, now that I've read it in R, my character is actually, it's a vector of character strings, right? So what is the length of this? Is a vector, just like you have a vector 1, 2, 3. But instead of having 1, 2, 3, I have strings. So what do you think the length is? Okay. So if I say length of my character, it's 3. So what is the number of characters? NC for the number of characters. Well, that tells you that the first is of length 2. It's a vector. The first is of length 2. The next one has 4. And the last one has 11. Okay, so these are some functions that you'll be using quite a bit. Now, where you can kind of get confused a little bit, suppose I create a character. I can create a character vector of 0. So if I do this, x is a character vector. It's created as character and a 0. What is its length? Its length is actually 0. And the number of characters, well, it's just saying it's integer 0. Now, a lot of times we do this, and then we sort of add stuff to it. So we may initialize something this way, and then we sort of push things onto it. Suppose I do, this is a little bit different. What is y? Y, by the way, whenever I put a hash, that's a comment for the rest of the line. So I have y equal, and then I have double quotes and nothing. So that's an empty character string, right? So what do you think the length is? Well, the length is 1. How many characters are there? Okay. In other words, it really is, unlike the above, where I said character 0, which had a length of 0, this has a length of 1. It is a character string. There's nothing in it. But I've had double quotes. Okay. So it has length 1, even though there's the number of characters in it is 0. I mean, that's a little tricky, but okay. Now we have substring. Now I can look at the substring of this, and since x, so let me tell you, I'm going to use another example because this example isn't particularly any good because it says, okay, this is sort of, I have a string and I'm going to go from the 2nd to the 4th position and subset it. So I'm going to do a substring. But of course there is no 2nd and 4th position because there's nothing there. So this is not a particularly good example. And the next two give you the same result. So I need to define x. I need to define x a little. I need to do something a little more interesting. So what I'm going to do is put, what did I call it? My care? Yeah, I'm going to put, instead of putting X there, I'm going to put my CHAR. Okay, well, let's look at my CHAR to compare it. So what did it do? Okay, it says that I have a string, and I'm going to subset it starting in 2 to 4, but it's going to do that for each of the strings within the vector. So in other words, notice that it goes from the second position. That first string only has 2, so it pulls back the S. There's nothing more. And then the next one, I'm going from 2 to 4. So I have soon, S-O-O-N. So what's the second position? O. Third is O, fourth is N. So it goes O-O-N. So that's why you have O-O-N. Now what about this? You go from the second through the fourth is that, right? So it's S space P. So it's subsetting, but it's actually subsetting each string within that character vector. So this is a simple function. There are other more sophisticated functions, but it gives us a way of subsetting. Now now there's also a substring, and the difference between those two deals with it deals like it's dealing with if I have strings that are sort of, I can have vectors of possible. In other words, I can have something like this. I can wrap 4, 5 times, for example. I can have sort of beginning. These don't have to be single numbers, and I'm going to show you this in just a minute. So what I'm going to do is, how much time do I have? Okay, I'll do this and I'll quit. This is a little bit interesting. RANDNA, what do you think RANDNA does? It generates a random sequence of DNA using the alphabet of DNA. So I'm going to it's going to be a length 102, so I'm going to randomly generate it. So let's just take a look at RD. And so this is the random sequence you get. You notice the G, T, A's, and C's are the letters of the alphabet. Now this is a random sequence. And so now, if you take random sequences and you take triplets of them, they map to certain amino acids. There's a process that you go from DNA to RNA, and then you can actually form triplets and go to amino acids. And so what I want to do is get a triplet. So I want to go from 1 to 102 by 3, and that's my start. Okay? And so we'll sort of see what we get, and I'm going to substring it. But I have another sequence that goes from 3 to 102 by 3s. So what I want to do is subset triplets of letters. So let's run this, and let's take a look at what we got. So the starting positions would be 1, 2, 3, then 4, 5, 6, because the ending positions will be 3 greater. So for the first starting position, I start. You can think of this as the end and this as start. So it starts at 1, and then it's gonna go from 1 to 3. Then the next time around, it's going to start at 4 and it's going to go 4, 5, 6 to 6. Okay, so it's going to go 1, 2, 3, 4, 5, 6. That's what's going to get subset. So if you look at this, the GTT is that first 3, and then the GAT, the GAT, is the next 3, and so forth. And so that's what it did. Now later on, he's going to show you a little function that can take this, which ran off the page, and make it so that it wraps. We'll talk about wrapping later. because we have this long sequence, and it could be very long. We like to sort of wrap it so we see the whole sequence. At any rate, now what this can do is this is taking this genetic code and mapping it to amino acids, and those are the corresponding amino acids. Okay. So it's taking this first one and maps to this, the second one maps to that, and so forth. Now, my intent, the reason that we sort of combine this undergraduate course, learning bioinformatics, with this course is because we're basically teaching R within the context of doing some bioinformatics. And, one of the big things you do in R, in general, is you may do text mining. Well, that means you have to manipulate text. So manipulating text is very, very important. So we're teaching manipulating text primarily a lot within the context of genomic type data. And as I said, it's very common that you want to do mining of genomic data, of these sequences, which is really text mining now. And that's actually a big area of research. How do you mine text? Obviously, if you're going out on the web and you're getting web pages and I'm looking for terrorists, I will use somewhat different tools than I would if I were doing genomic mining, looking for genes that may be related to a certain cancer. Okay, any questions? I'll stop here.